I had started off in my last slide, I spoke about the Ruby laser, which was the first solid state laser that I described. And here now I am going to describe the ND YAG and ND glass laser, which are also solid state lasers and very, very important, and they have tremendously large uses, okay, whether in industry or in medicine or in science laboratories itself. Okay. So, I start off with ND YAG and ND glass. ND YAG and ND glass are more or less close to each other, similar in many ways. Only thing in case of ND glass, that is an amorphous material, and ND YAG is a crystalline material. Okay. YAG stands for ytterbium aluminum garnet, which is Y3Al5O12. Okay, that's the chemical bonding that you have in that. And so the common part between YAG and glass is ND ions are embedded in this background of YAG, or ND ions are embedded in this background of glass. Okay. So these ND ions are sitting in different positions of the glass and YAG. Okay. You will come to know later on what are the small differences. Otherwise, mostly it is similar, like they have a similar resonator profile, which I have shown here. Okay. This is the ND, the active medium, which is placed here, and these two are the mirrors. One is the output coupler, and this is the 100% mirror, as in usual kind of resonator. Now, this active medium is like in gas lasers, the excitation was by the electrical discharge. Here it is by flash lamps here. So, that means light itself is exciting the ND ion molecules to different laser levels. Okay. So, it is not electrical discharge, it is flash lamp. Okay. So, here is a flash lamp shown here, and this is a flash lamp. So, you give a power supply which is supplies to this flash lamp and to this flash lamp as a schematic, and this shows the laser output. Okay. So, now let me just go through the energy level diagrams, which I have shown here on the left. Okay. So, these are not exactly to scale. So, I have not written any unit of measurement. I have just shown that this brown colored line is a ground level, and from here the excitation takes place, because these bands, this band and this band of the ND YAG rod absorbs the light that is coming out from the flash lamp, and they take all these molecules to the ions to the higher energy bands. Okay. Those are the absorption bands, and just remember that these are the energy levels of the ND ion. Okay, here that is embedded in YAG. Okay. So, they go up here, and some of them tumble down to this level, and then the lasing action takes place between these two levels, say, where lambda is 1.06 micrometer. So, ND YAG will lase in the near infrared region, and then there is a fast decay to the ground level. So, you can see this ground 1, 2, 3 and 4. So, it is a 4 level system. ND YAG, ND glass, both of them are 4 level systems. Okay. Now, in case of this this medium, the excitation of this medium, I have these flash lamps. Now, how are the flash lamps placed around the rod? You can see this is the rod. You know, the color of the rod is this light purplish pinkish color, depending on the doping of the ND ions in YAG or glass. Both of them have this similar, all this rod. So, this say this sort of a rod is placed here in the resonator. Okay. And it is surrounded by this flash lamp. If I take a cross section of this, this is what I will get. This is my rod, ND YAG rod, and this is one flash lamp, this is another flash lamp. referring to this one and this one. Now, this circular part, this I will not say circular, this elliptical part, it is actually a reflector. So, it is made out of generally some metal and the inside is polished, highly polished. So, that whatever light the flash lamp is giving out here, okay, nothing goes out, everything is reflected like this, like these lines here shown here. Okay. So, everything is reflected. So, so ND YAG will always come with flash lamp and its reflector. Otherwise, you are losing out all the energy which is going out here and there, and it is not using that energy, the light energy to excite those ions in the ND YAG crystal. Okay. So, this is one technical structure of the flash lamp pumping, light pumping. This is another ellipse. This is one more design which became very popular for a very long time. This is the ellipse which has two foci, one is here and one is here. One flash lamp is placed at one focus and the other ND glass is placed or YAG is placed in this focus. This design is very good because you use, say, you can make do with just one flash lamp. So, it is all how the thing is designed, you know. So, but then if the rod is quite large, then maybe you will need more flash lamps, larger in diameter, you will need more flash lamps. So, those are just some design thing, but in principle this is this placing the rod and the flash lamp at the two foci of the ellipse is a very efficient design. Okay. Nowadays, of course, you can pump it by diodes also, which makes it more compact and all that, but okay, to understand the basic principles of how it works, it is this is how it is done. Now, let us go to the emission and the absorption. Okay. So, I want to know which bands are these, which wavelengths are absorbed in order for the ion to move up to these levels, these pump band levels. Okay. Here, focus your attention to this diagram, which is the ND YAG emission picture, but ND YAG has pump bands at the 540 nanometer, 590 nanometer, 750 nanometer, 810 and 870 nanometer. That means all these wavelengths, around these wavelengths, somewhere close to these wavelengths, are all absorbed. Okay. So, this forms the absorption band. The ND YAG absorbs it very efficiently and it goes up to the upper level. Now, here I have shown the emission. As you can see, the wavelength is around 1064 nanometer. So, the center is around 1064 and you have a band of other emission wavelengths too. Okay. So, and this it is an experimental figure here, experimentally done, and this gives you the bandwidth, you know, this part here, if you remember what bandwidth is, and bandwidth is very important. Okay, this emission bandwidth. So, the difference between YAG and glass is just this emission bandwidth. Okay. Without going into the details, you just believe me that in case of ND glass, the bandwidth is larger as compared to ND YAG. So, they do have their own kind of uses. YAG, a smaller bandwidth has its own kind of use. Larger bandwidth can be used for obtaining very tiny pulses, very narrow pulses, which we will be talking about here. So, till now, when I have described, say, the ruby laser and carbon dioxide laser and ND YAG laser, I have not said anything about whether they are continuous wave or they are pulsed type. So, you get lasers which are pulsed as well as a continuous wave. So, we will know each of them have its own pros and cons are there. So, we will go about studying a bit about that. Before I do that, another very important solid state laser is the titanium sapphire laser. Okay. I did not show you any energy level diagram here, or it is similar to the previous one, say, or I did not show you the schematic of the resonator mode, which is pretty much what the other lasers also have. So, by now you are familiar. So, here what I show is the titanium sapphire, why it is very important. Okay. Titanium sapphire has a absorption band somewhere here in the blue and the yellow region. Okay, so you can see 600, 608 nanometer, all that, you know, the wavelength in nanometer, and its emission band is here, okay, somewhere close to the red and inching towards near infrared. Okay. So, as you can see, it absorbs in, and titanium sapphire is pumped by another laser. It could be a diode laser, or it could be a diodes or diode laser generally is used to pump titanium sapphire. And it has the speciality of titanium sapphire is its emission bandwidth is very, very large. Okay. It is very large as shown here. I have not shown exactly, but see, you can see the wavelength. It spans from around 600 nanometer to 2000 nanometer, okay, and it goes beyond also. So, it has a very, very wide bandwidth. So, wide bandwidths are useful for getting shorter and shorter pulses, okay, because time is inversely proportional to this bandwidth. Okay. So, a titanium sapphire is used in producing ultra short pulses. Again, as I said before, I will tell you what ultra short pulses mean, and its importance in various kind of uses. Okay. So, that is what I will be describing. These are all the lasers, though there are so many other lasers. This sort of gives you an idea of how to build a different kinds of lasers and what to look for in the active medium, or say in the resonator, in order to make a viable laser. So, here let me introduce to you pulse laser and CW laser. So, in case of CW laser or continuous wave laser, you just see this graph. This is the time scale, and this is the output. This is the lasing output. So, all through this time you are getting a single output. Continuously it is lasing. So, continuously you are getting an output. Now, what do I mean by a single pulse? You can have just a single pulse laser. Here in the time scale you see there is just one single pulse. It is not going in continuously, and this is the output. So, you have just one pulse. So, this has its uses, and the pulse also has its uses. So, this is a single pulse. Again, you can have another type of laser, which is a repetitively pulsed output. So, this is the time scale. You have one pulse, after a short time you have another pulse, after another short time you have another pulse. So, it goes on. Okay. Now, since you have this, you would look for an average power too. So, the average power will lie somewhere in this where this red dashed line is shown. So, here you have continuous wave, single pulse, and a repetitive pulsed output. Okay. Now, why do I need, in case of pulses, what are people bothered about? People are bothered about the average power here. Do you know what is the average power of the laser? And they are bothered about the peak power of the laser. That means, what is the power at this point? You know, and peak power is described as energy divided by delta T. So, here you can see, if you increase the energy of the laser, that means the output energy of the laser. I am talking only about pulsed. In case of CW laser, you do not describe anything as a peak power. Okay, there is only an average power. There is nothing like a peak power. You describe peak power only for a single pulsed laser. Okay. So, the peak power is E by delta T. So, either you increase the energy output of the laser, or you shorten the pulse. So, you have kept the energy constant, you have been able to shorten the pulse, okay, you will get a huge peak power. and huge peak powers are always sought after. So, ways and means and methods of making pulses shorter has described the last decade, or I should say 2 decades. People have just gone to extremes to make the pulse shorter and shorter, as I will be describing later on again, you will come across. Okay. So, now here I give the pulse repetition rate or frequency. Okay, it can be described as per second how many pulses are there, or in hertz. So, what do I mean by that? This is one pulse width, that is delta t. Okay, this is the delta t, and here there is no pulse, and again there is a pulse, and energy is whatever is there inside the area under this curve. This is power and this is time. The area under this curve gives you the energy, and if you divide by this pulse time, this much from here to here, you will get the peak power. Okay. So, here I showed the peak power is here, but the average power of, suppose this is a repetitive rate laser, there is one pulse, there is another pulse, there is another, what should be the average power, which will come in this level. Okay. This is easily understood. You have a period where there is a pulse, you have a period where there is no pulse. So, the average will always be lower than the peak power. Okay. It is like common sense. So, pulse repetition rate or frequency is equal to 1 by pulse period. Okay. This is pulse period. This is a period. It is like having a sine wave which goes like this, like this, like this, like that. Okay. So, this is a pulse period. So, I hope you have understood what laser power means, pulsed laser and continuous wave laser. Okay. Now, let us talk about the power. What is the power? How do I describe power? You have nowadays powers in terms of gigawatts and petawatts. Okay. And you have pulse duration which go from nanosecond to femtosecond. Okay. They are that large. Okay. Now, to give you just some of the terms that are used in this realm of peak powers and average powers and timing of pulsed lasers, here. So, if you have here in terms of power here, you have a megawatt power. So, in watt. So, megawatt is 10 to the power 6 and is given by the symbol M. Gigawatt is 10 to the power 9 and it is given by G. Terawatt is 10 to the power 12 and it is given by T. And petawatt is 10 to the power 15, which is given by P. So, all over the world people have reached around petawatt power level, not yet exawatt. Some laboratories in all over the world, in some places of the world, they have got exawatt, but okay, not confirmed. Okay, but petawatt is definitely there. So, if you can see 6, you add plus 3 becomes 9, you add plus 3 it becomes 12, you add plus 3 it becomes 15. So, it is that in the power it is just an addition of plus 3 plus 3 plus 3 and you go from megawatt to gigawatt to terawatt to petawatt. Okay. Now, at the same time I would like to show you what I mean by nanosecond to femtosecond pulses. So, femtoseconds are very short pulses, nanoseconds are pulses, and in 2024 nanosecond is quite large because and femtosecond is short, and beyond femtosecond you have the ultra short pulses. Okay. So, here it is microsecond given by micro 10 to the power minus 6, nanosecond n 10 to the power minus 9, picosecond is given by the symbol p. So, you can write ps, here you can write micro s or ns nanosecond, ps is picosecond and femto is fs. So, again femto is minus 15. So, what have you done to 6? You have added minus 3 and you got minus 9. To minus 9 you added minus 3 again, you got minus 12. To this you have added minus 3 again and you have got minus 15. So, you have this whole set of pulses which are in nanosecond and femtosecond. Okay. Now, in order to what I show here is, in order to increase the output energy E here, increase the output energy E, you have laser chains. So, till now I have described just one laser, a laser oscillator. So, a laser chain is something that you have an oscillator, and after that you have a whole set of amplifiers which forms the laser chain, okay, or they are called MOPA chains very often, master oscillator power amplifiers. So, you will have something like this is the oscillator, suppose, oscillator. Then the light from this is amplified into amplifier 1. The light from this is amplified into amplifier 2, and so you can go on, unless you have practical difficulties of having too much heat and being able to not be able to curb all that heat, you know, that those are kind of practical difficulties. But this is what a laser chain looks like. You cannot extract all the energy from just the oscillator. So, you need amplifiers in order to increase the energy, and if you increase the energy, your peak power also increases, as we have seen before. Okay, so, that is what happens. Now, for shorter pulses, so energy is one part and the pulse, the duration of the pulse is another part. Now, for shorter pulses, temporal width here I have shown as delta t. You can have pulse slicing, Q switching, or mode locking. Okay. I will go through all three of them in a bit of detail in the following slides. Okay. But pulse slicing is more of a mechanical effect. Q switching is one technique of extracting all the energy in a population inversion all in one go. It comes down in one go. And so, since all the energy is, you know, just kept there for a certain amount of time, and in one burst all that energy is thrown out. So, that is Q switching. Okay. And mode locking is a fantastic technique where the pulse can be shortened, okay, in case of mode locking. And mode locking, the shortening of the pulse here depends on the bandwidth that kind of laser sustains. So, if you have a larger bandwidth, very large bandwidth, as I have said in case of titanium sapphire, you do have a very large bandwidth, then you can extract shorter and shorter pulses. That is why titanium sapphire laser is an important laser. Okay. It is an important laser because the bandwidth is so large. Okay. Since the bandwidth is so large, you can get shorter and shorter pulses, and that is how titanium sapphire has become important in recent times. So, I will continue with the pulsed laser topic. A little bit more in details, I will be speaking about this pulsed laser topic, so that you understand the workings and everything a bit. So, as I had said, what is a single pulsed laser? Okay. So, here I show it with a graph because you will understand what is a single pulsed laser. So, here the blue line here is the gain, is a single pulse gain. So, this diagram pertains to the active medium gain. Okay. So, without a gain you will not get lasing action, and this is the red part of the pulse is the output pulse. Okay. So, this is the gain. The gain of the medium has remained constant, say, for this much time. Okay. The x axis is time and this is arbitrary units. Okay. So, this is how the gain has remained like this for this much time. Then all of a sudden in one go, this gain just falls down to 0. and the gain falls down to 0 means it has, that gain has to go somewhere, it just goes all into the pulse here. So, just when the gain goes down to 0, that means all the molecules are just tumbling down from the upper lasing level to the lower lasing level, and it is emitting, and your gain is going down and your pulse output is going out. So, in one burst of energy, in a time duration of say 40 to 80, around 40 nanoseconds, okay, from 40 to 80 if you see, so it is around in 40 nanoseconds, all your gain has become 0, all your energy is transferred into the pulse. So, this is how you get pulsed lasers. So, there should be some way, there should be, in order to hold the gain for a long time over there, and then in one big push you just put it into the pulse. Okay, that is the basic concept of a pulsed laser. Now, the thing is, what I want to show here is, suppose here you have got around 40 nanoseconds. You are not happy with 40 nanoseconds, you want to make it shorter than 40 nanoseconds. Then what do? You can slice out this pulse. You can slice out, say, this part, this long tail kind of a part, you can slice it out, and you can have only from 40 to 50 nanoseconds, that means 10 nanoseconds. Okay, you want a pulse of 10 nanoseconds, and you mechanically kind of slice out. How do you mechanically, I use the word mechanically, how do you mechanically slice out an optical pulse? It's almost like taking a knife and cutting it off, but an optical knife. Okay. So, what do? So, then once you slice out this longest part of the tail, you will get a pulse of this kind, which is very short. It is not exactly to scale, not exactly taken from here, just to give you the meaning I have just shown, a slightly narrower pulse in time. Now, how do you do this slicing? Slicing means you have to have some kind of shutter which is operating in that nanosecond scale. Okay. It's not easy to have a mechanical shutter opening and closing at a mechanical, if you think of any steel plate moving that fast. It's not easy. So, you have to think of some other means of doing it. So, what is this shutter or cutter? This is called a Pockels cell. Okay. So, you have this whole structure, this is a Pockels cell, and these are two polarizers. Okay. So, the input lasing beam is here, or lasing pulse is here. This is your laser which is incoming. It goes through the first polarizer, then it goes through a Pockels cell, and then it goes through another polarizer. So, this totality, this total thing is a cutter or a shutter. But how does it work? Here I will just give you a hint before I come to exactly how it works. So, the polarizer allows only one polarization of this laser pulse to pass through. It goes through this Pockels cell, where the polarization undergoes some changes. It becomes vertical, suppose it was horizontal, it becomes vertical, and this shutter does not allow the vertical part to go through. But the shutter will open only at a trigger of a different polarization. Okay. So, you have to manage that. You have to change the polarization at certain, this allows a certain polarization. You have to change the polarization over a certain time when this will allow. Okay. So, these two are like the gatekeepers, and the Pockels cell is the one which you just remember the name Pockels cell. I will give you the exact constituents of that. For the moment, just remember this, that these are two polarizers which is playing on the polarization of the light, and it acts like a shutter. So, that is what a single pulse is about. How do I get it? If you see the lasing part, so I have just given schematically the, this is a laser, this is the amplifying medium, and these are the two end mirrors. Okay. Just schematically shown, they need not be plain, they can be curved or anything according to your design. And these are the energy levels of this active medium, the amplifying medium. This is the ground level of the active medium. This is E1. So, from the ground level with pumping, whatever be the pumping scheme, it can be optical or electrical, anything. I am talking about a general laser. And you have populated the top level, the upper laser level. Okay. Everything from the ground has gone up because of that pumping or very intense pumping. Okay. And some you might have some spontaneous emission which is happening, but you try to avoid, you cannot really avoid spontaneous emission, but you are not allowing any stimulated emission. Spontaneous emission is perhaps getting lost somewhere else. Okay. But how do you prevent stimulated emission from happening? How do you take all the population over there and don't allow any of these atoms or molecules to tumble down here? You do it with a light modulator. So, this light modulator is closed. Okay. This is again like a shutter or a cutter, however, as I have said before. So, you keep on pumping, give some intensive pumping to the amplifying medium, and you do not allow any stimulated light to come through. You just store up all that energy in E1, and you build up the gain. So, suppose everything has gone up from the ground level, you have got maximum gain. Until that time, that light modulator is kept closed. You do not allow anything to go through to this mirror. The moment it goes through this mirror, it will revert back, and again you will get stimulated emission, and this process of back and forth will go on. You stop just that. Then in one big strike, you just open this shutter. The moment you open this shutter, all these molecules will just tumble down to the lower laser level. And you will have this path between the two mirrors going back and forth, and it will be amplified. And you will have some laser output here. So, in one big shot, all of them come down in one big pulse before the light modulator closes again. That is how you get a single pulse. You do not allow anything to come out before that single pulse. And the whole, the upper level is saturated with molecules, saturated with all this energy. And the moment it gets that shutter open, that energy is transferred into this stimulated light, and you get one single pulse with a huge amount of energy and very large peak powers, of course, depending on the time which it takes to do that. Okay. So, here it is. So, this is the whole mechanism of a shutter, okay, of getting a single pulse. Next, we see what is a mode locked laser. Mode locking is a very, very important part of pulsed lasers, because it comes out as a repeated laser pulse, but again the shortening of the pulse depends on the bandwidth, and it is happening on its own. So, sometimes you can call a mode locked laser to be a repetitively pulsed laser too, but how does this mode locking work? So, here again I have the active medium, okay, and I have these two mirrors, and okay, my pulse is rotating here and there. And in each round, what do you do? In each round trip, you let one round trip happen, and the active medium is building up. In each, at the end of one round trip, you open the shutter here. Till now, I have not described what this shutter looks like. It is a very special shutter. It is definitely not a steel mechanical shutter. It is an optical shutter, which has a certain mechanism to it. Okay. So, this is what the shutter looks like. Okay. And then you have a pulse which is coming out here, emission of parts of the pulse at each round trip. Now, again in the second round trip, again this shutter modulator opens and then closes, and again you have one more pulse. So, with this each round trip, you have described a a distance between a time distance between the two pulses. This is constant, this round trip is constant. At every round trip you are getting one pulse, second round trip you have another, third round trip you have another pulse. So, it is quite, it has a repetition rate which is regular, and the spacing between the pulses also become regular. You know, you could, mode lock pulses are very, very regular like this, and this distance remains constant. C by 2L quite often, not yet here. So, this distance, this distance, this distance is depending on the round trip time. So, that is what mode lock lasers are about. So, till now I have spoken about this, I have just put everything together here, single pulse laser, single pulse Q switch repetitively, and mode lock pulses. And here, if you are interested, you could see some of the uses of these kind of lasers. I really will not go through them, because my main aim will be to tell you exactly how all these things work. So, I end my lecture here, and in my next I will be talking about a bit details about the actual design of some of the optical components which gives you these kind of pulses.